Hello everyone, this is lecture 17 of 465 and 531. Today and Wednesday will be our review, and the exam will be on Friday, Friday the 11th of October. And it will be a different exam for 565, 465 versus 531. There is some common questions and some different questions. So it's not it will be two documents. When you go to PTRE to take the exam, it's gonna be two documents. Make sure you open the right one. Make sure you follow all the rules. And in all honesty, I don't know all the rules. Don't get yourself in trouble when without doing something to get in trouble, you know? It's like I had somebody the first year that I was teaching, first semester, I was completely new in the process, totally green, and they sent me a report for a student who was writing on his hand something because he didn't have scratch paper available, and I realized that was an honest sort of, I stopped the issue from escalating, and I make sure that you guys have scratch paper, but you have to destroy it, I think, after the exam. So I sorted that out. But last year we had somebody cutting connection before submitting and then submitting it all by himself, and this is a no-no because that's how they shouldn't. You guys shouldn't have access to the exams after the exam time is up. So follow those instructions that you have for PTRE, and I know it's a little bit of a pain in the rear, the whole PTRE situation, and I think we are gonna change system, and it's gonna be, I think it will be, School of Engineering will be the last one. College of Engineering and Mines will be the last one to change. I don't know the new system, what it's gonna be called or what it's gonna be about, but I was told so. Okay. So the exam will cover the entire module 1 and module 2 up to what was slide 40. And it was, especially module 1 was pretty hierarchical. That means we started simple, we got complex, then we got a little bit more simple. And then module 2 was a little bit, it was, I know, a little bit dry, a little bit too mathematical, but it's stuff that we have to know moving on. And I promise you that module 3 and 4 are gonna be more interesting. They are more applied, more down to stuff that we do. I mean, if you are a graduate student, probably you will find module 2 pretty useful because you are, if you are working on doing any kind of geomechanical modeling or any kind of mechanical modeling, in all honesty, it will be useful. Oh, I forgot to tell the TA to grade the homeworks, but I need to send him the solution key. I know that the homeworks were, homework 2 was due on Friday, midnight. And I will try to get the TA to grade them as fast as possible, but he is very busy with something else. If he cannot grade them by Wednesday, I will upload the solution key. But what I do when I upload the solution keys, I go to Blackboard and I see whoever hasn't submitted yet, and I give them zeros. So I try to give a few days to some people if they haven't submitted to be able to submit it even for half, 50% of the grade, you know? Anyway, so I can do the review with whatever format you want. If there are specific questions, I can answer them, or I can go through the slides very fast and try to point you towards the important stuff. And if there is questions along the way, I'm more than willing to stop and discuss items. I try to give hints throughout the class. This is an important topic. This is not an important topic. Yeah, I mean, I think if you are on top of it, you will do very well. What is geomechanics? We talked about, gave the definition and several applications in our world. Our world, geomechanics has more than petroleum engineering applications, more than what it does in petroleum engineering. It has a lot of applications. It's geotechnical, which is a subdiscipline of civil engineering. A lot of chemical engineering even applications can have, certainly structural geology applications, and geology applications in general. As petroleum engineers, we are really focused on what happens near the wellbore and in the reservoir in general. So this is the focus that we are giving this class, which is geared towards petroleum engineers. We talked about structural geology. We basically want a model that will relate deformation to stress. And deformation, we said, is a little bit of a qualitative term. Displacement is more quantitative, but we use strain, which is dimensionless. And yeah, we talked about magma currents underneath the lithosphere are not balanced, so you have a dynamic sort of situation which changes with time. What else? Faults and faults with D, we talked about those. Divergent plate boundaries and convergent plate boundaries. We talked about the difference between being tectonically stressed environment and tectonically relaxed. Tectonically relaxed, think about normal faulting. Tectonically stressed, think about strike slip and reverse faulting. When you see mountains, you are close to reverse faulting and stuff. If you see a delta environment, if you are at the coast and there is a river, the mouth of a river, those are very normal faulting stuff. Tectonic movement induces stresses, and gravity has impact, a lot of impacts. The way the rock behaves, its ductility, ductility and brittleness, these are not exactly antonyms. They are antonyms in the English language, but technically, I think the chair has a very strong opinion about high ductility doesn't mean brittle. Sorry, low ductility doesn't mean brittleness necessarily. Anyway, we are gonna see, generally speaking, the rocks that we deal with are quite brittle. That's why we do hydraulic fracturing. They basically break in a brittle manner, in a tensile manner. Anyway, and of course, we have fluids in the pores of the rock. They are under pressure and they exert pressure everywhere, so they affect the normal stresses that we mentioned earlier. Generally speaking, we have in the subsurface, we have 3 mutually orthogonal stresses that are compressive. And we call the most compressive S1, least compressive S3, and the intermediate S2. Those are at 90 degrees with each other. Some papers, they use S3 for the most compressive, so make sure that you check the nomenclature of what you are reading. I use the same, I try to use the same nomenclature that other classes in petroleum engineering, in geomechanics of other petroleum engineering departments are using. I use about the same nomenclature as Nicolas Espinosa uses in University of Texas, and Canvu is using at the University of Texas A&M. And I think what John also used to use in University of Texas. So we try to be as consistent as we can with each other. But generally, S1 is the most compressive, S2 is the intermediate, and then you have least compressive. And the only difference, the main difference with your other classes, like solid mechanics, is that in solid mechanics, you have tension as positive and compression as negative. Here in rock mechanics, in the subsurface, because we have way more compression than tension, we just reverse it so that it doesn't, we don't end up with too many negative signs and get confused. These stresses can be used to indicate how the stress was in the past. People who do paleo stress modeling, there is a professor in a petroleum geology professor now in the geology department. She's doing paleo modeling, but using chemical indicators. This is mechanical indicator. By looking at the stress, we can tell in the direction of faults, anticlines, this kind of stuff. We can tell what was the stress in the past. And orientation, faulting, natural fractures, focal mechanism, etc., etc. We can say a lot about the past. Dikes with I is basically hydraulic fractures. They are hydraulic fractures made by molten rock. So the way they break the rock and the magma breaks the rock and pushes through is basically what we try to do with our fluid during hydraulic fracture treatment. So batholith, dikes, this kind of stuff, they are tensile failure. Earthquakes and slippage along pre-existing fractures, which we are going to see a lot in the next module, module 3, is shear failure mechanism. And it's we're going to talk about that a lot in the next module. And I think homework 3 will be about those. So it's important to know what kind of failure you are dealing with, not so much at this stage, but later on as well. So how do we measure those stresses? The easiest to measure is S3 because it's the smallest one. And as we learned later on in the module, when you have a tensile fracture, it opens against this S3. So if I try to make a tensile fracture, I open against S3, okay? And if I do a leak of testing in my well, that's what I'm trying to do ultimately. I try to get to the point where I'm just about to open this tensile fracture. So I'm trying to beat this S3. What people call a hydraulic fracture test, maybe fluid-driven tensile failure test is a more technical name. 3 of those are the extended leak-off, mini-frac, step rate test, a lot of variations of that. And also a lot of those are controlled by the state legislature. In Texas, you are mandated, if you are drilling an injection well, to run a, what do they call it, not a step-down test, a step rate test. So if you go to the Texas Railroad Commission, which is the state entity that governs oil and gas activity in Texas, has nothing to do with trains. It's historic reasons why it's called the Texas Railroad Commission. It used to be the first, when they were overproducing in the 1930s, and they needed people to enforce production quotas, make them choke the well so it doesn't produce for some days. And they were producing behind people's backs to make money. they have to send an entity that has a lot of manpower, and they send the Texas Railroad Commission. And that's why even now, if you are voting for a Texas Railroad Commissioner, you are voting for somebody who is going to oversee the oil and gas activity. Now, if you are voting, if you want to vote somebody to see the trains, is the transportation department, whatever. TxDOT, whatever they call it in Texas. Department of Transportation.
DOT, yes.
Yeah. Mini frac, extended leg off, everything gives you some way or another an indication of S3. And then, of course, the stress state is very complex in the subsurface. The normal stresses are not aligned in the principal directions, and you didn't know what that meant when we first saw this slide, but now that you know what comes afterwards, you understand what it means. You have shear stresses because, and this is a matter of perspective. Generally, you will use tensors to indicate the stress state. In 3Ds 3x3, in 2Ds 2x2, and there is some mathematical processing that is necessary to get the principal stresses and their directions. And you spend a lot of time on your homework doing that. Remember, it's a matter of perspective. I rotate my frame of reference a certain way, and I get all the shear stresses to zero out. Therefore, what I have on the normal stresses is the identity of the matrix, is those principal stresses. And perhaps if you are running an experiment, you need to do this analysis so that you make sure that you want to have a matrix like that rather than like that. Because when you do the analysis of your experimental results, these will make more sense, easier to manipulate. Not make more sense. Now you can use that, and basically you can use that and be do it correctly, but it's going to be much more complicated processing, mathematically speaking. And this is the equation that you are solving to get the eigenvalues and the eigenvectors. We had an example here. I expect you to know how to do eigenvalues and eigenvectors, but don't expect something crazy, because remember we said that for stability in the Earth's subsurface, the tensor, the stress state must be diagonally symmetric, which makes our math a little bit easier. In the homework 1, all the tensors I gave you were unstable. So they were harder than what they had to be. But now you know that it needs to be diagonally symmetric. So if I put a mirror on the diagonal of the matrix, what I see on one side, I should be seeing on the other side. That's how I have stability. If I don't have stability, it means that there must be some sort of motion going on, taking place, which means that the stress state is unstable and it will eventually become stable. Okay. Example problem number 1 is important. This is how you find the eigenvalues and eigenvectors. Eigenvalues are the in situ principal stresses. Eigenvectors is their respective directions. For every eigenvalue, you have an eigenvector, right? Okay. Now rotation matrix to special reference frame. I don't want you to care about this for the exam, okay? Because I just want you to know what is it used for, know how is it used, but don't expect a mathematical problem in a 50-minute exam using this matrix. I'm not stupid. I mean, it's I mean, it will become, don't worry about matrix rotations for this exam. Now, at that point of the class, things became very, very mathematically complex. So we brought in Anderson from 1951 to make things simpler by saying, what if I say that one of those three stresses that you said earlier, S1, S2, and S3, is very, very close to vertical. And we call that SV. That means the other two would be very, very close to horizontal. So we call that SH max and SH min. And we apply only one rule. The SH max must be bigger or equal to SH min. It cannot be smaller. So that way, it simplified our concept quite a bit. So I just have three stresses. They face at the same direction. Sorry, a fixed direction. So one is vertical, two are horizontal. Of course, the horizontal can be anywhere in the horizontal plane, but on the plane perpendicular to SV. But always SH max must be bigger or equal to SH min. That's our rule. If we honor that, we're gonna have three possible regimes, which you probably learn about in geology, introduction to geology class. I don't know if they make you take that here, but back in my time, they made us take, we started in the fall semester, and they made us take introduction to geology before we take introduction to petroleum engineering. And I started by taking petroleum fluids class, physical and chemical properties of petroleum fluids. So I learned how to do like flash calculations and this stuff. And then I had to take an introduction to petroleum. Anyway, so the first permutation is where you have SV bigger than SH max, which is bigger than SH min. That's normal faulting. Gulf of Mexico is a very good example. Tectonically relaxed environment. The other one is the opposite of that, which is SH max being the biggest, SV being the smallest, SH min in the middle. This is reverse faulting or thrust faulting. That's like where you have mountains, Himalayas. New England is not very mountainous. And the west side of the US is mountainous, but it's more strike slip than reverse faulting.
And the north part is like reverse thrust, it's like compressive.
Yeah, I know in Canada it becomes, yeah. So anyway, New England, Himalayas, yeah, reverse,
Japan
yeah,
next.
Australia. And then you have strike slip, which is the west coast of the US. San Andreas Fault is excellent example. You have SH max being the biggest, SH min being the smallest, and SV being in the middle. And we have this hanging wall and foot wall that help us understand the motion taking place. I'm not gonna go in very detail here, but if you see the lectures that we talked about it, I think we did a pretty good job explaining the three Andersonian faulting regimes. And then we collapsed everything into one value, which is the alpha phi. Oh, A phi. Because Lunster was calling it A phi in the lecture he gave the other day. I was talking to him about it, I said alpha phi, and then I realized he was saying A phi. But anyway, one equation that basically for normal faulting, n is 1 or 0. For normal faulting, n is 0. For strike slip faulting, n is 1. For reverse faulting, n is 2. And the result is that for normal faulting, you have alpha phi, A phi, 0 to 1. For strike slip faulting, you have alpha phi 1 to 2. For reverse faulting, you have A phi 2 to 3. And then it goes Dr. Lundstern, who took this scheme, this scale, and he colored it a certain way, and he gave us those beautiful stress maps, which is basically gonna be the new generation of the world stress map. And I think he's gonna become very famous for those maps because they are very useful, very very good looking. And actually, he gave us a presentation last week, and he said, if any of us want a specific portion from the world stress map that he makes for our papers, to reach out to him, and he's willing to help us, which was very nice of him. It's gonna be nice to have on your paper something like that because it's like imagine figure one of your paper having something like that is very nice, and he's very open, giving permission to us to use this as a in our work. One interesting thing that he said a lot of interesting things, but for this module, he said that if you go deeper, the stress magnitude changes, of course, but AFE doesn't change as much, he said. It stays more or less the same, which is very nice for us because it sort of takes the depth out of consideration. Like
The colors stay the same.
the color stays the same, the stress increases. It's pretty convenient. Yeah, and visit his website. It has a lot of stuff that can be helpful. Okay, don't worry about this other than knowing how it doesn't work. Like we took we simplified the rotation matrix for each stress regime. So the RPG had the very ugly form, and now we took it for each stress regime and we simplified, and we are left only with one angle alpha, which is basically the azimuth. Okay. And now, how do we evaluate the magnitude of SV? This is an important set of slides. This is an important topic, okay? Because there is many ways this can be done, okay? You are ultimately trying to solve this equation, this integral, and you approximate it with this summation. Now, there is several ways you can be given the data that you are dealing with. You may have a stress log, and you get the density from there. You may have I don't know, different information. You saw one way in the homework that was pretty generic, but there is several ways. Ultimately, what you are trying to do is to measure how much does the earth weighs above you. Okay, and the weighing, as in pound mass, can very easily become force, pound force. And then the area it's acting on, inches square, pound per inch square is PSI. So for every foot depth, you have a certain amount of PSI accepted. And the logical assumption can be 1 PSI per foot. So if you are calculating an SV, you will expect it to be in the order of 23 MPa per kilometer or 1 PSI per foot. So I wouldn't be very surprised if I find 1.1, 1.2, 0.9, 0.85 even. But I would be very surprised if I find 3 PSI per foot. It would be crazy, right? It would be illogical. Or 0.3. It would be very small, right? Now, if you are given the density and the layers are stacked vertically, you can use this. What if it's a mixed rock that is composed of sandstone, limestone, shale, and you are given the density of each, but they are not vertical layers?
Sorry.
You have a rock, say that it's like partly sandstone, partly limestone, partly shale,
Okay,
and you have the density of each,
okay,
but the proportions.
okay.
Can you find the SV?
You can see fine, yes, you do the sum of all the mass,
Depends on the.
You do the
how much
weighted
you-
average of all the densities.
yeah.
Say I have limestone is 2.71.
71 to 76, it depends.
Yeah, limestone, yeah, dolomite is 2.87.
Eight, it's from 78 to 85, 86.
Okay, so if I tell you that the rock is 20% this, 70% that,
And you can do the
10%
average,
that, you
yes.
can do the average of the density.
Yeah.
Okay,
But you said like it's not layering, it's like.
yeah, it's mixed.
Like it has like a different like.
No, it's mixed like.
It's a mixed rock.
Oh,
It's not
a
like
mix.
that.
Ah, okay.
It's not like
Okay.
that. It's easier than this actually,
Yeah.
the problem.
Yeah.
Okay. What about if you are offshore? Huh. I have the top of
You have
the.
water, different density of
Yeah.
water, so.
Just remember, you only need to add the water depth on one of the layers. Don't do it on every layer.
Yeah,
Then you are
because
double
then-
counting.
It's like you have different dogs.
I had some people last year, I think they were doing the homework together and they ended up doing the same mistake. They found a huge value because they were adding the water on top of every layer of the earth underneath or something. It was a different homework. Huh? Yeah.
Under the beach, there is
A typical value for the seawater gradient for Gulf of Mexico is 0.4465.
And they sink under the water.
they swim under, they have
Yeah.
a beach under the beach.
Oh, really?
That's
Yeah.
possible.
I don't know. Yeah.
And they
That was
stink.
after my time.
Yeah.
Uncle Scrooge was better.
Wait, they sing underneath the mud line, let's say?
I mean, their whole life is under the sea. And they have a beach under the sea, they rest
Oh,
on.
yeah.
And they sink. Some people want to swim and they sink there like.
Oh,
Yeah.
they can have a pool
Yeah,
under the sea.
They have put it in the sea. Yeah.
they have actually a real beach like here in Malibu, California.
Oh, wow. Yeah. For reference, freshwater gradient is 0.433 psi per foot. So the salt adds weight.
It's kind of one of the paradoxes.
Yeah.
Yeah. It's like Tom and Jerry.
Yeah,
You know,
yeah,
all the time they
yeah.
when they
Yeah.
go to swim, they wish on.
Yeah. Good days. I always think of the cartoons towards the end of the year, December, during Christmas time.
Yeah.
That's when they all came out, right? The good days. 1940s, I think,
Yeah.
or late 20s, mid.
20s was Charlie Chaplin.
I think Mickey Mouse came in 28.
Really?
Yeah.
I thought it came in the 40s.
No, the Donald Duck and those people came in the
40s.
40s.
When DC started though.
Huh?
DC.
What's this?
Like the Bond, the DC, like the Bond, DC, you know, Batman and Superman.
Oh, those were later.
Later.
Much later.
Oh.
Those were much later. Must be.
And Marvels and stuff.
Yeah, those were later. Yeah, because I didn't catch them in my childhood. Oh yeah, we had Batman, I guess.
Because it was famous, like in my old, my dad's age.
Yeah.
I was like 60, 63 or something. The 70s it was famous.
Must be.
Superman.
Yeah, but Superman was a movie and
Superman was later, was in the 2000s.
huh?
Superman,
No, Spider-Man.
Yeah, those were,
no, it's Marvel, it's not like.
Yeah, it's not easy.
yeah. Anyway. Yeah, that about SV. And then we started talking about the fluid inside the pores of the rock. So this fluid is under applying pressure on the rock's pore walls, right? Applies pressure equally in every direction. It needs to be taken into account in our modeling considerations. So you basically have to include it in your model. We said the 0.433. We talked about some stuff, hydrostatic equilibrium. And then we talk about how do we compare the water, the pore pressure in a rock versus the hypothetical freshwater density. No, it's not hypothetical, it's actual freshwater density. If I'm above, I'm abnormally stressed, right? If I'm exactly like that, I'm hydrostatic pressure, also known as normal pressure, and I can be under, I can be above. If I'm over pressure, it means I have bigger than the freshwater density equivalent. Pore pressure at the pressure higher than the freshwater equivalent. Now, this is an assumption that you should not make. If you have a reservoir of a depth so-and-so, don't go and assume hydrostatic pressure gradient and tell me that I don't have any indication of the pressure, so I do 0.433 times depth. And again, that would be a very bad assumption to make. Okay. Pressure traverse plots we talked about. Yeah, that's what you see on the left. And you build some in your homework 1. And there are several mechanisms in which you can get over pressure. And we talked about those. The most important one was the one I did when I was drawing the New Orleans Delta and basically showing how does the sediment gets deposited in stack sequences. And then you have the fluid wanting to escape and go upwards, but it's escaping slower than what it's getting stack sequences. So you end up with the sand getting stuck. So you end up with what we call overpressure. And that's why we look in Gulf of Mexico for a lot of hydrocarbons at high pressure there. Changes in temperature can make overpressure. Diagenesis, hydrocarbon generation in itself creates overpressure. Don't kill yourself with this theoretical, don't memorize a lot of stuff unnecessarily, just know how to, what they are, but don't like know every detail, okay? Disequilibrium compaction is what we talked about, and we gave you the example. Very, very important. And then you can have also under pressure, which is the opposite of overpressure. Reservoir depletion, human activity can be the cause. Compartmentalization in reservoirs is a big real world concern because you have models, they assume 100%
reservoir connected.
yeah, everything is connected, and then you find parts are disconnected for whatever reasons. You may have a fault or something. Then there is the model.
Geology discontinuity.
Yeah. Then the model is not giving you the right results because it doesn't have that. Then we said, how do we incorporate pore pressure in these equations? And we said, okay, pore pressure acts in every direction. So we are going to have pore pressure subtracted from each of the principal stresses. and it was basically it led to a new set of terms that was given by the Greek letter sigma. S became sigma. Sigma incorporates pore pressure. So sigma I is SI minus PP. And the rank remains the same. Sigma 1 is bigger or equal to sigma 2, which is bigger or equal to sigma 3, because pore pressure affects each stress the same way. But they are smaller. I expect sigma to be smaller than S, and the difference of the two being pore pressure. Can you have a negative pore pressure?
No.
No.
Oh,
I said, no.
It's like vacuum.
Yeah.
yeah, how do we get-
Yeah, I said, can you? But he
Oh,
said no,
okay.
and I was like, yeah,
Like the quality.
yeah. It would
The
be,
reverse.
yeah,
Like there is nothing pushing, it's like something like
yeah, it cannot be. Or you stick a
Like-
vacuum pump and you,
Yeah, it's like popcorn in the microwave.
huh?
Popcorn in the microwave.
Yeah, yeah, it's, and then we had this compaction index from homework 1. We said it's good for shales, and there is a reason why when they look for,
consolidated sandals.
yeah. When you are looking for a high porosity, can be an, if you look for a high porosity indication, it can be a presence of high pressure, overpressure. We saw that in the homework. And we had a lot of discussion about it. I'm not gonna go into too much detail on that. And this is how a pressure traverse will look like for each stress regime: normal, strike slip, reverse faulting. Remember, you start by tectonical relaxation, and you become more and more stressed as you go from normal to strike slip to reverse. And none of the compressive stresses should be bigger or bigger than the smallest of the three. So I cannot have pore pressure bigger than S3, right? Then I will have a negative sigma 3, which would be, it means that I'm lifting the
It
F.
can be equal at some point, but not.
That means I'm having net equilibrium on that side.
Yeah.
Yeah, net equilibrium. Because there is a lot of compression in the subsurface, you may have 0 for a little while, and then something else will come and push eventually. You may have, yeah, it's a little bit extreme to have low compression. Generally speaking, in the Earth subsurface, for the depths we are looking at, is strong compression. And then the most important part of this module is this. How do fractures, tensile fractures open? And we spend a lot of time talking about those. This is important. How do fractures open? I can say there will be in the exam. This is something that is going to be on the exam, one form or another. How do fractures open? They open in one direction and propagate in one plane. You need to know. They open against S3 and propagate in the plane of S1 and S2. Lusten actually didn't say it right. He said they propagate along SH max and they open against SH mean, assuming normal or strike slip faulting. He should have said they propagate again in the plane of SH max and SV, because they propagate as a plane, they're not propagating as a line, right? But I mean, assuming that SH max is smaller than SV, it would be more moving in the SH max direction than height wise. That's why he simplified it like that. But all the stuff that we drew in the exam, in the lecture, we drew about,
So that's only in two regions, right?
no, we talk about three different regimes.
No, talking about this. This is like normal faulting and
Doesn't matter, S1, S2, S3. It depends. And we talked about transverse and longitudinal with respect to the wellbore fractures, and I was using blue for transverse and red for longitudinal, and these are important. So remember, a fracture, say this is a vertical well. Okay, let's see a longitudinal fracture.
What people want.
From a vertical well.
Yeah.
Okay. What is the direction of SH, S3?
S3 was that one, the opening,
This one?
the width,
And then I have two more
the plan.
for the plane. Which of the two is S1 and which of the two, which is S1, which is S2?
This is S1, this is S2.
Correct. Excellent. Excellent. And this stuff you need to be very, very comfortable with. Or we also have transverse. Okay, this is more like, well,
Can do it for you.
yeah, I want to do it in 3D. Oof. Okay, I will do it. I will do it only at the bottom, but I will exaggerate a little bit. So I have a Zoom call at 3:45. I hope nobody shows up at 3:30 here, so I can. Let me make it. The fracture is very, very tall, but slim. I don't know if I. Oops,
Yeah,
sorry.
it's okay.
Enough to show to people. First, when you see something like that, ask yourself one thing. Okay, how did the fracture open? How did it open? Against what did it open? It opened against S3. So this one is S3. So you are telling me now the S3 is parallel to the lateral, to the well, right?
yes.
So, and then you have two remaining. You have this, and then you have this. Which one is S2? Which one is S1? Yep,
Yeah.
correct. So this is S1, this is S2. I want you to be very, very comfortable with this stuff. Yep. Oh, and then we talk about leak-off testing, and I remember I drew a leak-off test, and we talked about when do fracture start, and we said the fracture initiation. We said like how is, if I can.
If you want it, it's open, when it closes.
Yep. We had a lot of discussion about time, pressure, and then it goes like this, and then at some point you stop increasing linearly,
Yeah.
you start going like this,
Yeah, yeah.
and then if you keep
Yeah.
going, then you are gonna drop down, and then propagate like this, and then you stop pumping, and then it goes down initially ISIP, and then FCP, But in leak of testing, we don't go all the way to failure. This is the leak of pressure. This is the breakdown pressure. And I told you all the way here, I will draw it green. I can have fracture initiation at any point. Here. Any point. I can have fracture initiation. At any point. So what I do is I will pass the leak in the oil field when I do leak of testing. I don't want to get fracture initiation. I'm not yet doing a fracture. This is for a fracture. But if I do a leak of test, I will stop pumping at some point. It will drop. I will get the ISIP and then the FCP. ISIP. And I told you there is a lot of controversy. What is S3? Is it the ISIP? Is it the leak of pressure? Is it the FCP?
Or the tangent between.
Yeah, the truth is, all of them are pretty okay indicators of S3, but they are not, there is no definitive one. For this class, I said ISIP, because general is the highest of the three, and you want to get the highest value to be on the safe side. So I give you basically the highest value
The minimum value.
or the minimum value. No, FCP would be the minimum.
Yeah.
Yeah.
The minimum value.
Yeah, it depends.
It's not really-
In drilling, we are doing FCP, I think.
Yeah.
Yeah. And this one is geared towards the next class is basically stimulation.
Oh.
So yeah,
Your
yeah.
maximum?
Yeah, they want the highest. Well, really, they are all very close to each other. What I was gonna say, I forgot. Oh yeah, notice leak of test is S3 that is telling you, not SH mean.
Yeah.
So
No, it
for
can be
reverse
vertical.
faulting, what is it telling me? Yeah,
Can be in reverse faulting S3.
it's not SH mean.
Yeah.
It's
Can
not.
be SV.
Yeah, SV. But SV, I know it from something else, right? The overburden estimation, maybe. So don't expect, some people say, I get SH mean from leak of testing. Yes, most of the time, not universally.
Okay.
I cannot go to Vaca Muerta in Argentina. There are parts that are reverse faulting. There are parts that are strikes, but, and then tell them, oh, leak of testing, that means that's your SH mean. No, it's not your SH mean. It's your SV.
S3.
Yeah, it's to be general enough, you need to say leak of testing is giving me S3.
So you can get your SV without the cockpit. You can get your mud window.
Yeah.
Because functional.
You can't get it from one window, yeah.
Yeah,
No. I mean, your mud window, you can get it from SV only, right?
your mud window, yeah.
So you no need for remote. I mean, no need for that.
Yeah, but
Yeah.
it's gonna be a different indication, I think, if you have fluid versus if you have the stress load. So you may want to run that to be on the safe side.
Because you will just use the same pump and everything, just you will pump some you need the same equipment of drilling, right?
Yeah, you do it during drilling. You pump mud,
Yeah, pump mud. You have the mud and you have the pump.
but you know, even you will change the mud density and you get a different value of
But no,
everything.
using the same mud because
No, no, no.
you dedicated that mud to drill that formation, basically.
Yeah. It's better to do it with the same stuff. Yeah, but if something changes, the readings change. I mean, it's very sensitive, right? It's very sensitive.
So I missed it. For the purpose of this course, we're using ISIP for our estimating S3.
Yeah. Let's use ISIP. You may not even have this dilemma in exam time necessarily, but
McClure uses.
yeah, I know McClure doesn't like tangent method. Tangent method gives you a very
Underestimate. Because you're going below.
it gives you very high, because you use that value SH mean to get the fracture pressure, the net pressure inside the fracture.
Mhm.
And then you're gonna have a very low SH mean. That means you're gonna have a very high fracture pressure. Higher than what it really is. That's why he doesn't like that. But there's a lot of discussion going on about that. Yeah, Justin, let's use ISIP. But I think you're not gonna be in a dilemma like that in an exam or something.
Okay, thank
So I
you.
think you'll be fine. Anything else? It's 3:29. If they are not waiting outside, I can stay until 3:35. I have a Zoom call at 3:45. That's the issue. And then next class, we are gonna do the module 2 up to slide 40. But yeah, this stuff, the most important thing we did, I think, is how do the fractions operate? Yeah. And this example problem number 6 is useful. We saw how the wells are drilled. Why you want to drill the wells facing to the laterals towards the horizontal laterals in Texas towards the Gulf of Mexico, and in Louisiana north to south, because that's the direction of SH mean in those areas. What I was gonna say, I forgot. Forgot what I was gonna say. Yeah, the way the fractions open is a very important topic. And of course, other stuff as well, like the Andersonian. Don't get intimidated if you see eigenvalues and eigenvectors, because, like I said, stable stuff are easy matrices. What you saw in the homework was a little bit of a harder than what it needed to be problem. Some of the equations that we saw today, like the approximation for the overburden, the integral is always the same, okay? But the approximation here is like, it's something made for this kind of problems. Don't expect it to be, like, you need to be, don't be sclerotic, like, this is how I'm gonna get the problem and this is how I'm gonna solve it. You need to adjust based on the data that you have. In the homework, you saw the water of the seawater having a variable density, and you had to adjust your equations accordingly. I gave an example today of what if the rock is mixed, not in vertical layers, but like mixed as a whole. You need to do the weighted average based on the proportion of each rock, right? But this doesn't make the things harder. It should make them actually easier. Yeah. I don't remember what else would be in the exam, but and I haven't finished the exam, to be honest. I put down some stuff, but yeah. And these videos, today's lecture and the next lecture, is gonna be on a separate folder. I will call that midterm exam 1 review. And it's gonna be yellow color. And I will have them separate those videos. Anyway. And with that, thank you very much. Justin, any other questions?
No, not right now, but thanks.
Okay, sir. Boys, any other question? All good? Okay. Thank you, guys. I will see you on Wednesday. We are gonna go through the part of module 2 that is gonna be on the exam.
Thank you.
Thank you, sir. Stop sharing. Stop recording.